start to see the pattern. So this is sort of condition reinforcer here. What's the probability that the guy, for example, missed arm numbers 2 and 3? That's the same problem. Just collapse them, tie them. It becomes one arm. But the number of the other remaining options is k minus 2. So this means that the guy has sampled from the other k minus 2 arms for n trials. So on one trial, that probability is k minus 2 over k. Over n trials, it is this. What is true of arms 2 and 3 is true of any other pair of arms. So I take advantage of symmetry. And so here's a solution. That's the probability, and that's the sum. There are k pairs 2 at a time. So now you get the picture. Notice the pattern. The combinations are k 1 at a time, k 2 at a time. You guess what's coming up next. K 3 at a time, k 4 at a time, up to k. What about there? You have k minus 1 over k minus 2 over k minus 3 over k minus 4 over k. And there is a beautiful pattern here. I've just filled the table completely. And you stop here at 0. Okay? So if you do it systematically, there is no way that you're going to do more terms than needed. We plug this awful looking formula. Yeah, we can write it in a more concise way, but remember, this is not what we want. That's the opposite. So I need to subtract this from 1. I get that, and each one of, I mean, this looks awful, but you can compute one by one, and that's the solution to the problem. Some people see beauty where some see windmills, others see giants. So, okay, so we can write it in a more abbreviated form. This is just a redescription of what's there. And then we plug the entire thing. We have divided the problem into parts. We have figured out the probability of each part. Let's recap what we have done. What did we want to learn? We want to find out, to learn what's the probability that after n trials, the number of distinct arms equaled k. We fixed attention on k-specific arms. We determined the probability that these arms are the set of arms visited during the n trials. This is the hard part. And then, of course, this is just for k-specific arms. Well, we have combinations of 8k at a time. We put this together and we have our solution. So, remember, the formula looks like this. Number of ways of choosing k arms times the probability of visiting only the set of k arms times the probability of visiting all k arms. I have to sample from that set of k, and I have to ensure that I sampled each one at least once. So, we plug the numbers, and Excel can do it, and I get the distribution for the radial arm maze. And you could compute the average. Intuitively, we look there and see the average must be around here. Alton and Schlossberg refer to 5.25, and you can check that number right on the mark. They get it right. But I'm going to jump here. We could do the same thing for Ellen Nuringer's results, and the number is correct. The nice thing, because it's the same thing, it's the same problem, except that Ellen was working with a radial arm maze with 256 arms. His problem is exactly the same. Okay, so we have checked. Oh, hold on. This was just a recap. So I'll go a little bit faster. Sorry about this. I should have removed this. Okay, I want to conclude with the following thought. Many students, when taking statistics courses and probability courses, have told me, for example, oh, I'm a little bit upset. I mean, the teacher only gives us these problems with coins being flipped, balls being placed in urns, and I was interested in the psychological problems. My reply to these students has two parts. The first one is, I understand that. Go back to your instructor, and I'm sure he or she can give you examples of how this applies to psychology. But do not despair. Many problems have the same structure. If you learn these problems that these guys have included for decades in introductory textbooks on probability, there is a good reason for them to be there. They have a structure that is similar. So if you learn the structure, and then you vary that's the type of problem, you abstract the structure, and then when you see these problems, they have all the same structure. The solution to one is a solution to the other. So this is just like the radial arm maze. Or if you want, a radial arm maze is just a cereal box problem. This is a famous one. And it's the Ellen Nuringer's problem, if we assume that pigeon is pecking randomly. It's just the same thing with 256 arm. So I'd like to conclude returning to the Marquis, who said, regarding the science of probability, Laplace concluded that there is no science more worthy of our meditations, and that no more useful one could be incorporated in the system of public instruction. I doubt his first statement. I think psychology is still more interesting, but I fully agree with the second statement. Thank you. Yes.
This is all very complicated for me. What's wrong with just simulating all of these results?
Good point. There's nothing wrong with simulating. There is something wrong with only simulating. First of all, simulations can take time. Simulations are parameter dependent. And I have simulated many times because I wasn't able to solve the thing. So one nice thing of this, it develops your intuition and it gives you precise results. For example, given the final result on the distribution that we saw for the radial arm maze, I plug a different number of arms and I get, for Alan Neuringer's case, with 256. I can not only get the mean, I can get a confidence interval. And I have, for example, observed that in one experiment that Alan and Page did, all the birds were within the 95% confidence interval of distribution. You could get that by the simulation. There is little in discrete probability they cannot simulate. But then you need to run lots of trials. And I don't think you get sometimes, unless you run lots of simulations, play a lot with it, you don't get the intuition. What is this parameter doing? What happens if I change this parameter? Number of trials. And I think there is also an element of fun for some people. So I think intuition, deeper understanding of what's going on, you could get it by simulation, but sometimes it takes a long time.
Matt, so how do you think about spreading the probability out over time?
I'm not sure I understood the question. What do I think about spreading the probability over time?
Yeah, because if I conceptualize my problems predicting what the organism is going to do at 2 o'clock next Wednesday afternoon, looking at it as a temporal space, defining where something is, then I'm going to be able to think about how it's looking.
Well, that's a different sort of a type of problem I have not dealt with in one tutorial. I restricted my attention to discrete probability and more to very simpler cases like, this stat pigeon is choosing the keys with the same probability, or the stat rat that is choosing the arms. And what I think it's important there is, I don't know of any rat that behaves like this, but it gives you a reference point. For example, when Schlossberg tells us that their rats took, after 8 trials, visited on the average 6.5 to 7.5 distinct arms, I know what random would predict, 5.25. I can compare it with the rats and say, gosh, these guys are really much better than what randomness predicts. But different sorts of models would lead us into continuous time and serial dependencies, and these are much more complicated. I didn't deal with them here. Matt?
Armando, what other tricks do you have in your bag? So you talked about conditioning on the first step. You talked about
counter-variables.
Repeat the question.
The question is, what tricks have I illustrated here or do I have in my bag? Sometimes I didn't name them, but one of them is certainly expectation by conditioning. That generalizes to probability by conditioning. When you have multi-stage experiments and you want to compute the probability at the end of them, you can say, okay, let's see what happens on the first trial. And many times you get recursive, like in the expectation. That's the first. Second is counter variables. One variant of the counter variables is what's called indicator variables, variables that can either be 0 and 1, and they are beautiful to count. I didn't have time to illustrate. The other one is compute the opposite of that probability. The fourth one, if you want, break the problem in parts. Those are the tricks.
I think we don't have any time for any further questions. Thank you very much.